Hi, my name is John Bodner. I'm a software engineer at Capital One. I've been programming for most of my life. Since the 1980s, I've used a lot of computer languages. I've started writing a list of all the ones I'd used, and I got to around 25, and I still think I forgot a few. And right now, I'm doing as much Go as I can. I like Go. Among other things, I like the fact that it feels like the Go team thought about how features would interact before they implemented the language. Go feels put together rather than grown, and that's not always the case with programming languages. But, and this is true for Go too, if there's one thing I've learned that all languages have in common, it's that they all have these little things that just don't quite work the way you'd expect. Those little things are at first annoying, because after all, your program didn't behave the way you thought it would. But on second glance, those little things are actually really interesting. They tell you something about how the language is put together under the covers. They help you peer inside to the implementation. So who here is familiar with the WAT talk that Gary Bernhardt gave at CodeMash 2012? Awesome. Yes, if you haven't seen it, wait till after I'm done, and then go to www.destroyallsoftware.com/talk/what and take a look. So in about 4 minutes, he goes through just a few of the weird things that Ruby and JavaScript will do. So for example, in JavaScript, adding an array to an array equals empty string. Adding an array to an object returns an empty object, but adding an object to an array returns the number 0. And adding an object to an object returns not a number. Seriously, try this out sometime. So yeah, what? And this is all really funny, right? Because the things that make no sense. And I've used all those languages at different points in my career, but I've mostly worked in type languages like Java and Go, and there's a certain sense of smugness because my favorite languages don't do these weird things. Well, sort of. All right, so at work we have a Slack channel dedicated to Go where experienced Go developers split their time between reminiscing about the good old days of 8-bit computers and answering questions from new Gophers. And really, one of the best development communities I've ever been a part of. But what I found is that some of the questions that we get from these new Gophers are things that are not obvious bugs. They're places where everything makes sense if you understand the underlying concepts and implementation. But at first glance, they're just as weird as adding together an array and an object. So I started to realize even though Go is a pretty simple language with a pretty well thought out feature set, it still has its share of whats. And I started to collect them and thought I would share them with everyone here today. So before we begin, I'm going to point out there's absolutely, positively nothing new here. If you've seen these sort of puzzlers before, that's great. If you haven't, I hope you've learned a couple new Go corner cases that you can avoid in your code. Also, rather than just go through a litany of weird things for 40 minutes, I thought it would be good to make this a bit of a game. So periodically, I'm going to stop and ask what you think the result's going to be of some code, and I'll ask you to vote by raising your hands, and then I'll tell you what the right answer is, and we'll see why Go does what it does. So let's start with slices. We all love slices, right? So one of the first things you learn about slices is that they are a reference type, like a pointer, and you can pass a slice to a function, and you can change the values in a slice. So you can write a function to, say, double the values in a slice, and this code works. When you run it, it'll print out 1, 2, 3, and then it'll call double vals and print out 2, 4, 6. So you can pass a slice to a function, and you can change its values. But what happens if you try to grow a slice in a function? What is this code going to do? All right. So let's do some voting. A, does this not compile? Who thinks this code is not going to compile? Anyone? Okay. B, who thinks the code's going to panic? Anyone for panic? All right. C, who thinks the function call does nothing? It prints out 1, 2, 3 twice. Okay, good, good. And D, who thinks the function call is going to work? It'll print out 1, 2, 3, and then 1, 2, 3, 4, 5, 6. All right. Okay, a couple people. All right, well, the correct answer is C. It prints out 1, 2, 3 twice, and the function call does nothing. And if you look at the code, you'll see that line s equals append s456 in the grow function. And the way the append function works, it checks to see if there's enough capacity in the slice to add the new values. And if there is, it returns the same slice. But if there isn't, a new slice that can hold all the elements is made, the values in the original slice get copied over, and the new slice gets returned. And since we passed in the slice with length and capacity of 3, that means we got a new pointer here, so of course it didn't change in main. And we can confirm this by using the fump.printf function and the %p verb to get the pointer for a slice. And we're going to print out 4 lines. Before we call grow, at the start of grow, at the end of grow, and back in main after grow. And sure enough, if you run it, you'll see that the values of the pointer change inside the function. So it makes perfect sense why you can't see the longer slice. The pointer and values are the same on lines 1, 2, and 4, but on line 3, we have a different pointer, and we have a different value. So I mentioned that the capacity of a slice is big enough, then append returns back the exact same slice. Well, you can set the capacity for a slice. So if we change the lines that create and populate the slice in main, maybe the code will work. So what is this code going to do? Does this A, same 4 choices, does this Not compile. Anyone say not compile? All right, that's pretty good. All right, B, who thinks it's going to panic? Anyone thinks the code is going to panic now? All right. C, who thinks the function call still does not work? Prints out 1, 2, 3 twice. Okay, and D, who thinks the function call is going to work now? It prints out 1, 2, 3, 4, 5, 6. Oh, the answer is C. It prints out 1, 2, 3 twice. And if what makes it even weirder is we put back in those print statements to display the pointer value alongside the actual value, you'll see the pointer value is the same on all 4 lines, but the contents of the slice are only different when we're still inside of grow. So the pointer doesn't change, but the value doesn't stick. What? So what's going on? As a shorthand, we say the slices of reference types, which makes it sound like you can treat them just like a pointer, but that's not quite true. So to figure this out, let's visit the Go runtime. If you're not familiar with the term, the runtime is a library that's compiled into every Go program. As the Go fact says, the runtime implements things like garbage collection, concurrency, and stack management. It's not a virtual machine, just a library that provides critical language services, and that includes slice support. And in runtime slice.go, you'll see how Go defines a slice. A slice is actually composed of 3 parts. There's an unsafe pointer to the data, an int for the length, and an int for the capacity. And that unsafe pointer is the reason why a slice can hold data of any type. The runtime has special support to convert unsafe pointers back and forth to regular pointers. And when we make a new slice, the Go runtime calls the function makeSlice, and that takes in a reference to the type and the length and the capacity for the slice that we want to make. And then inside of makeSlice, we allocate the memory for our pointer and return back our slice. Now, Go is a call-by-value language. When Go makes a function call, it always makes a copy of the values that are passed in as parameters. So if you pass a pointer to a function, you're making a copy of the pointer, which points to the same data in both functions, lets you modify the data in both functions. When you pass a slice to a function, you're making a copy of the slice, which is this struct with 3 values in it, and then you assign that to the function parameter. So we can understand why we can change the values in the slice, but we can't lengthen the slice. When we create and populate that slice in main, we created a slice struct with a pointer to the allocated memory, the length field, and the capacity field. When we pass the slice to grow, we created a copy of the struct, which points to the same allocated memory, but has its own copy of the length and the capacity. And at the end of grow, we have put the new values in the allocated memory, and we've updated the length field to 6 in our copy in grow. But when we exit grow, the copy of the slice just disappears, and the length field in main is unchanged. The values are still there in the allocated memory, but we can't see them in main because the length field tells us there's only 3 values in the allocated memory. So you might be wondering, if we have a copy of the slice in the function, why does func.printf say the pointer stays the same? Well, that's because Go lied to you. When you ask func.printf for the pointer to the slice, it gets the pointer value from the value.pointer method in the reflect package. And the reflect package has a slice header struct that's like that slice struct definition in the runtime. And anyway, value pointer doesn't give you the memory location of a slice. It gives you the memory location of the pointer to the slice's data inside the slice. And since that's copied to the function with the length and the capacity, that's why it stayed the same. So if you want to write a function that changes the length of a slice that's passed into it, you have to make the parameter a pointer to a slice. And really, this is the only situation where you want to make a function parameter a pointer to a slice. So let's move on to the other built-in data type, the map. What is this code going to print out? We declare a map. We read the value of hello from the map, we assign 20 to hello in the map, and then we read back the value for hello in the map. What is this going to do? Does this A not compile? Who thinks this code is not going to compile? Anyone? Okay, B, who thinks this code is going to panic immediately? Any votes for panic immediately? Okay, got a couple. All right. C, who thinks it prints out 0 and then it's going to panic? Okay, and D, who thinks it prints out 0 and then prints out 20? All right, well, the correct answer is C again. It prints 0 and then it panics. Declaring a map variable with a var creates a nil map. And you can read from a nil map, and that gives you back the value of the map, the 0 value for that value for the map. But writing to a nil map, that causes a panic. And just like we looked under the covers to see how a slice works, we can do the exact same thing to see how maps work. And see why I get 0 back for a nil map read, but a panic for a nil map write. In the case of maps, there's 2 things to look at. So say you have a map called M, and you're reading from or writing to a key called K. In your code, write v : m sub k to read from the map, or m sub k = v to write to the map. And in both cases, you have this map access, m sub k. And when the compiler runs, the code in the walk expression function in the file compile internal gcwalk.go gets called. It looks at the map access and figures out if it's on the left side of the equal sign or the right side. And if it's on the right side, it's a map read, and the compiler converts the code you wrote to a call to the runtime function map access1. And if it's m sub k is on the left-hand side of the equal sign, compiler knows it's a map write, and it substitutes a call to the runtime function map assign instead. Both map access1 and map assign are defined in the Go runtime, in runtime hashmap.go. And remember, we call map access1 for reading from a map. Function checks to see if the map is nil or empty, and if it is, returns a 0 value. And we write to the map assign is called at runtime, checks to see if the map is nil, and if so, it panics. So let's look at another thing we do with maps. We iterate over them. What is this code going to print out? So we put a bunch of keys and values into the map. We then create a slice. We then iterate over the map. We copy the keys into the slice, and then we print out the slice. What's it going to print out? A, did the keys print out in the order they were inserted? Who thinks that's the case? A. Anyone for A? All right. Okay, B, who thinks the keys were printed out alphabetical order? Anyone at all for alphabetical? I thought someone would go for that. C, reverse alphabetical order. Anyone feeling really daring here? No? All right, we'll get one. Great. And D, who thinks we have no idea? All right, very good. Yes, the answer is D, we don't know. So maps in Go are, in computer science terms, hash maps. For those who aren't familiar with the term, here's a really quick, mostly true overview. So a hash map does fast lookups of values based on a key. And each key is turned into a number using a hash algorithm, and that number is then mapped to one of a set number of buckets. And then the key and the value pair are stored in the bucket. And each bucket can hold more than one value. If two keys map to the same bucket, that's called a collision. The keys and the values for both are stored in the bucket. And in this case, we have a collision between K and K3. You don't want to have too many collisions because the more collisions, the slower the hash map gets. And there are clever hash algorithms to avoid this, and hash maps can grow. And they're really useful things to have, but they're hard to get correct, so it's great that Go includes one out of the box. So anyway, the order for iteration for a Go map is unspecified, so be sure not to write code that depends on iterating through a map in a particular order. Now for a follow-up question, how many different ways will Go iterate through the exact same map? So this code iterates through a map with 9 elements 1,000,000 times and counts all the different iteration orders. So what numbers are going to print out? And this code does work correctly. So A, 1. Who thinks it's exactly one iteration order for a map? Okay, good. B, who thinks greater than 1, less than or equal to 20 different iteration orders? Okay. C, who thinks greater than 20, less than or equal to 10,000? Okay, got some of those. All right. And D, who thinks greater than 10,000, less than or equal to 1,000,000 different iteration orders? All right, well, the correct answer is B, between 1 and 20. So if Go allowed every possible iteration order, you'd expect something like 9 factorial, around 360,000, but that's not what happens. When I run this program on my own computer, it usually outputs 10, sometimes 12, rarely 14. And this is kind of weird, right? So what's Go doing with map order? Well, when Go was first released, the iteration order for items in a map was usually, but not always, the same if you inserted the same items into the map. And this caused 2 problems. One, people would write code that assumed the order was fixed, and this would break it in inconvenient times. And 2, if maps always hash items to the exact same values, and you know a server is storing some user data in a hash map, you can actually slow down a server by sending it specially crafted data where everything hashes to the exact same bucket. This is a real attack called hash DOS. And to prevent both these problems, the Go team modified the Go runtime to do 2 things. One, when a map is created, the runtime picks a random number and uses this random number as a seed for every value that's hashed. And 2, every time a map is iterated with a for-range loop, a different bucket in the hash map is chosen as a starting point, and a different item in the bucket is chosen as a starting point in the bucket. And you can see the code for this, again, in runtime hashmap.go. So the underlying type for a map is a struct called hmap, and it has a field called hash0. And the makeMap function sets hash0 to a random number. And every time there's a map read or a map write, hash0 is passed to the hash algorithm. And when a map is iterated in a for-range loop, the function map iter_init is called. And in that function, there's code to pick which bucket to start from and which item in the bucket to start with as well. And the reason you don't see the 360,000 different iteration orders is because iterating isn't just going randomly through the map. It's going through the order in the buckets, but it just picks a different starting point. All right, before we move on, one last map what. We've seen what happens when you pass a slice to a function, but how about when you pass a map to a function? What is this code going to print out? So we have a equals 10, we print that out, we call add stuff, we say b equals 20, and then print out the map again. So what's this going to do? A, does it not compile? Anyone think it does not compile? One of these isn't going to compile, you know. All right. B, does this panic? Who thinks this code is going to panic? C, who thinks the map stays the same, that both times it says A equals 10? All right. And D, who thinks the function call works? It says A equals 10, this says A equals 10, B equals 20. And yes, that is correct. The answer is D. If you pass a map to a function, you can add or modify or delete the items in the map, and the changes are visible in the calling function. So why is it different from a slice? It's because the functions in the Go runtime that make slices and make maps, they return different things. When a new map is made, the make map function is called. It returns a pointer to hmap. The make slice function that's called when a new slice is made, that returns a struct, not a pointer to the struct. And since map is really a pointer to hmap, the pointed to data is visible in the calling function. Okay, enough about data structures. Let's look at one of Go's more unique features, named return parameters. So a named return parameter lets you specify a name for a return parameter as part of the function signature. You can set the value for the return parameter and then rather than specify the value as part of the return statement, you just leave a blank return and it works. And you can write something like this. So this code works correctly. You run this code, it'll print out 10. And now that we know how these things work, what is this going to do? So rather than take advantage of the blank return, we assign the named return parameter a value, and then we return an entirely different value. So what's this going to do? Does this A not compile? Who thinks this code is not going to compile? Okay, B, who thinks this is going to panic? Anyone think this is going to panic? All right, got a panic vote? All right. C, who thinks it prints out 10? That the value assigned to result wins. Okay, and D, who thinks it prints out 20? The value in the return statement wins. And yeah, the answer is 20, D. You set the value of a return parameter, and you specify a return value. The value that's specified as part of the return statement is the one that wins. So if you use named return parameters, be careful. All right, there's another unique feature of Go. There's defer statements. Oh, did we move on to defer statements? Oh, all right, yeah, we were good. We're at defer statements, right? The first statement lets you register a function closure to run when the current function exits. We usually use them for cleanup of things like open IO readers, open IO writers. And defers almost always run. So the only way I know of to keep them from running is a call to os.exit, and please never call os.exit. So what happens when this code is run? We have the same code we had in the last example, only now we have these two defer statements also. And in the first defer statement, we add 1 to result, and the second one, we multiply result by 3. So what's this code going to do? Does it A, print out 20 again? Who thinks it prints out 20? All right, B, who thinks it prints out 31? All right, C, who thinks we get 33 this time? All right, got a 33 vote. And D, who thinks it prints out 61? All right, a couple for 61. All right, well, the correct answer is D. It prints out 61. What? How did that get returned? So there's a few things going on here. First, even though we say that defers run after a function completes, it's a bit more accurate to say that the defers run right before a function exits. And second, we have 2 defers. When you have multiple defers, they run in reverse order. The last one of your function is the first one to run. So we're going to triple the value of result, and then we're going to add on 1 to it. But the defer is referring to result, and we're returning back 20. And if you do the math, it doesn't make any sense. Result wasn't there. So why do the defer statements do this if they only refer to result? So Go does something interesting here. If you have named return parameters and you specify explicit values after on the return statement, Go assigns those values to the return parameters. So there's actually an invisible result equals 20 in the code. And so let's walk through this. First, we assign 20 to result on the return statement. Second defer runs, and we multiply result by 3. That triples it to 60. First defer runs, adds 1 onto it, you get back 61. Function finishes, we go back to the main program, and we get 61. So unfortunately, the code that implements this is a little too complicated to go through right now, but if you want to look it up yourself, look at the end of the state.call method in compile internal gc ssa.go, and you'll see the code that defines the order that defer statements run in. And you can see the values being assigned to named return parameters in the walk statement function in compile internal gc walk.go. So on to another completely different source of what's. What is this code going to do? So main has a colon equals 1. We have a for loop. The first line of the for loop says a colon equals a plus 1. And then the second line of the for loop has a equals a times 2. And then after the for loop, you print out the value of a. What is this going to do? Does it A, not compile? Who thinks this code is not going to compile? All right, optimism, that's great. All right, B, panic. Who thinks this code is going to panic? Something might panic. C, who thinks it's going to print out 1? All right, got a bunch for 1. All right, and D, who thinks it prints out 94? Anyone for 94? All right, well, yeah, the answer is C, it prints out 1. And that's because Go has block scope. It allows you to define new variables with the same name within a pair of braces that shadows or covers up the variables from outer scopes. So in effect, you have 2 variables with the same name. On the line a colon equals 1, we have a variable called a at the top level of the function. On the first line inside of the for loop, we have the a colon equals a plus 1, and those are actually 2 different a's. The a on the right-hand side of the colon equals is the a from the top level of main, and the a on the left-hand side of the colon equals is a brand new variable that's going to be visible to the end of the block. And because we got this new variable a inside of the block, on the next line, a equals a times 2, the a on both sides of the equal sign is this new variable a. And each time the loop runs, we create a brand new block local a. When the loop exits, block local a ceases to exist. When we print out the value of a in the top level of main, we get 1 because we're seeing the top level a, and we never actually modified it. So let's see what happens when you combine shadowed variables with named return parameters. What is this going to do? So we call what shadow, we pass it 50, we say ret equals I times 2. If ret's greater than 10, we say ret colon equals 10 and return with a blank return. Otherwise, return from the top of main. From the top of what shadow, sorry. So A, does this not compile? Who thinks this code is not going to compile? Okay, good, good. B, who thinks this code is going to panic? Anyone here for panic? All right, C, who thinks it prints out 10, that the inner ret is going to win? All right, and D, who thinks it prints out 100, the outer ret is going to win? I got you this time. The answer is A, this does not compile. What? Why does that not compile? So what's interesting is the compiler error message. It says ret is shadowed during return. This is the only place I'm aware of where Go doesn't allow you to shadow a variable. If the shadow has the same name as the named return parameter, and there's an empty return in the same scope as that shadow, in that one case, you can't get it back an error message. And you can see the code for this in compile internal gc noder.go in the noder statement fall method. Cutting out a bunch of the code from this method because it's really big, but this method's job is to run some basic sanity checks on the statements in a block of code. And if it finds a return statement, it checks to see if it's a blank return. If it is, it checks all the named return parameters, makes sure that none of them are currently shadowed, and if any of them are, it returns back an error message. All right, let's take one more look at shadowing. What is this code going to do? So we're not returning from that inner block, but now we're going to put a defer in there instead. And so we have a defer that has ret equals ret plus 1 inside of the inner block. So what is this going to do? Does this A not compile? Anyone now think it's not going to compile? All right, B, does it print out 11? Okay, a couple of votes for 11. Good, 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 some 11s. All right, C, does it print out 100? Does the top level ret win entirely? Okay, got some 100s, good. And D, does it print out 101? All right. Correct answer is C. This prints 100. And the reason why the code compiles is because the return is no longer in the same scope as a shadowed variable, so it doesn't care anymore. But the closure that the defer is running, it's declared in the inner scope. And when it increases the value of ret by 1, it's referring to the inner ret, not the outer one. And since the closure is referring to the inner ret, the outer ret is never modified. And when your return runs, it returns back the doubled value. So I haven't given a lot of coding advice yet today, but please don't use shadowed variables. They are, in my opinion, a design mistake in Go. So there's a flag for Go vet called -shadow that will check your code for shadowed variables. Make sure you run it, remove any shadowed variables that it finds. All right, completely different topic. What is this program going to do? 2 lines. We say a colon equals math.maxuint64, and then we print out the value of a. Simple enough. Does it A, not compile? Who thinks this code does not compile? Okay. B, who thinks this code's going to panic? I'll keep putting it up there. All right. All right. C, who thinks it prints out the max value for unsigned 64-bit ints? Not going to read that number off. All right. And D, who thinks it prints out the max value for a signed 64-bit int? All right. One brave person. A couple of brave people. All right. Well, the correct answer for this one is, yeah, this does not compile. You get back the error message, constant 1-844-6744-073709551651615. Overflows int. What? Why does Go think A is an int and not an unsigned 64-bit int? Well, constants in Go are a little weird, especially integer constants, which includes runes. And they're a little fuzzy in their whole concept of type. And that lets you assign any integer constant to any integer type as long as the integer type is big enough to hold the value. So you can write code like this. We assign a rune h to this variable of type byte. This compiles, it runs, prints out 104, the Unicode value for lowercase h. But if you specify an integer constant that's too big to fit in a specified type, you get a compilation error. And here we're assigning a rune with the value of a smiley face emoji to a byte, and this fails the compilation error that constant 128512 overflows byte. So integer constants aren't just numbers or single character literals either. Go supports constant expressions which contain mathematical operators. And if you look at the definition of the various integer limits in mathconst.go, you'll see that they're actually expressions. And none of those constant values is specifically assigned a type. They can be assigned to a variable of any integer type in Go as long as the type is big enough to hold the value. But what happens when you use a constant with type inference? We write things like a:0 all the time, and that 0 is a constant. If those integer constants don't have a type, how can Go infer what type you assign to A? And even though constants don't have a specific type, they do have a default type that gets falled back to in cases of type inference. So in the case of integer constants, the default type is not surprisingly int. For runes, default type again, not surprisingly rune. And for floats, the default type is float64. So now we see how these parts fit together. Since math maxun64 is far bigger than the maximum value for an int on any platform, it overflows at compilation time, we get our error message. If you want to assign math maxun64 to a variable, you have to explicitly declare the variable to be of that type. All right, another completely different topic. Let's say we have a program with the following struct defined. We have this t that says empty struct. We've defined a method on pointer to t called num that just returns back 2. And in main, we declare a variable t that was a pointer to t. We print out if t is nil. And then we print out the result of calling t.num. Simple enough. What is this program going to do? Does that A not compile? Who thinks this code does not compile? All right. B, who thinks this code is going to panic? Got some votes for panic here. All right. C, who thinks this prints out true and prints out 2? All right, a lot of people for that one. And D, who thinks it prints out false and prints out 2? The t is not equal to nil. All right, the correct answer is C. It prints out true and 2. So we have a variable that's nil, but we can still call methods on it. What? So this is one of the more interesting things about nil in Go. I don't know of any other language that lets you do this. If you have a pointer receiver, a method defined on a pointer to a type, and you invoke the method, as long as the method doesn't assume that there's a non-nil value for the receiver, the method call will work. And this is kind of neat because it lets you write certain algorithms in a much simpler way. So Franz at Campoy actually gave a talk at GopherCon a couple years ago called Understanding Nil, where he talked about all the things that nils can do in Go. And really check it out after my talk. Franz plugged it this morning, actually, too. So on that note, let's look at nil some more. What is this program going to print out? We call error1, we declare a variable error of type error, print out if it's nil, return it, then back in main, we print out if the returned value is nil. Simple enough. What's it going to print out? Does it print out A, false and false, where error is non-nil inside of error1 and in main? Okay, B is print out false and true, where error is non-nil inside of error1 and then magically nil inside of main. Okay, C, does it print out true and true, where error is nil inside of error1 and it is nil back in main? All right, good. And D is it print out true and false, where error is nil inside of error1 but is non-nil in main? All right, well, the correct answer is C. It prints out true and true. So error is nil inside of error1. Error is nil when we return back to main. So let's try something else. We're going to define another really simple type, myError, implements the error interface. We're going to call error2, declare a variable error of type pointer to myError, print out if it's nil, return it, and then back in main, we'll print out the returned value is nil. So what is this code going to do? Same 4 choices. Does it A, print out false and false, where error is non-nil inside of both functions? All right, B, does it print out false and true, where it's non-nil inside of error2, but it's nil inside of main? All right, C is print out true and true, where it's nil inside of err2 and it is nil inside of main. Or D is print out true and false, where it's nil inside of err2 and it's non-nil inside of main. All right, well, the answer is D. It does print out true and then false. Even though error was nil inside of function err2, it magically becomes non-nil when you return it back to main. What? So I wouldn't be surprised if every Go programmer in the room was bitten by this at least once, right? So what's going on? The really short version is that nil means different things for an interface than for other types. And the longer explanation is a little bit more involved. In order to understand this, you have to understand what interface is represented in Go, what it means to assign a value to an interface, and what it means for an interface to be nil. So first, to talk about nil. Nil is a weird thing in Go, and really it's weird in all languages of the concept of nil or null. It's really a hole in the type system because you can assign nil to all bunches of things and compare it to them and set it to them, but you can't set and compare those things to each other. So behind the scenes, the Go compiler and runtime does things to make nil work correctly across types. And there's actually a special nil type that means untyped nil, which is like the other untyped literals we saw earlier for numbers. It can be assigned to all sorts of other types and becomes those types. But the rules for assigning and comparing to nil are different for interface types and for concrete types. So let's talk about interfaces next. Go represents an interface as two parts, a tab and a data. The tab consists of two parts, an interface type, which is the list of the methods that define the Go interface, and the underlying type, which is the concrete type of the value that's been assigned to the interface. And the data part of the interface is that value for the interface. And given this, let's see how nil works with interfaces. When we use var to declare a variable of interface type, and error is an interface type, you get an instance set to the 0 value of the interface. It has a data field with the value set to nil. It has a tab with the interface type set to the interface's type, in this case error, and the underlying type set to nil. When a variable with a concrete type is assigned to a variable with an interface type, the value of the concrete type is assigned to the data field in the interface, and the type of the concrete type is assigned to that underlying type field in the interface's tab. So in this case, our concrete type's value is nil, so we get nil for the data, but the underlying type is set to pointer to my error. Now, when a variable of interface type is assigned to another variable of interface type, Go does something slightly different. It copies the value of the original interface value to the value of the new interface, but it copies the underlying type of the original interface to the underlying type of the new interface. Go will never wrap one interface type inside of another interface type. So you can see in this example, we have nil underlying type and nil value in error1. So when we assign error1 to error has the nil for both underlying type and for data. And finally, we have the rules for comparison for interfaces, for instances in Go. And there's 3 general rules. When comparing two variables that are both concrete types, you only compare the values to determine if things are equal, and that's because the compiler won't even allow you to compare two variables with different concrete types, so all you have left to compare is the value. When comparing two variables of interface types, you compare both the underlying type and the underlying value. Both have to be identical. And what's interesting is the interface types don't need to be identical, though. As long as one interface contains all of the methods of the other, the two interface variables of different interface types can be compared. So finally, when comparing two variables, a variable interface type with a variable of concrete type, you compare the concrete type with the interface's underlying type, and you compare the values of both variables. If both the types and the values are identical, the two variables are identical. So now we have all the parts to understand what's going on. In error1, we have a variable of type error, which is an interface. We don't assign it a value, so the tab's underlying type is nil, and the data is nil as well. We compare it to nil, we check the underlying type and the underlying value, both are nil, so this prints out true. When we return this value back, it's copied to the return value. We get an error interface instance with an error for the interface type, nil for the underlying type, and nil for the data. And in main, we have our error variable of type error. We compare that to nil. And we compare error to nil in main. We see that it has nil type for the underlying type and nil for the underlying value, so we print out true. In error2, we have a variable of type pointer to my error, which is a concrete type. When a concrete type is compared to nil, the value is compared to nil. In this case, that's true. However, when the value is returned, it's converted to an instance of an error interface. And this error interface instance has nil data, but the tab has an interface type of error and an underlying type of pointer to my error. And this time in main, we have an error variable of type error, but comparing with nil has a very different result. the underlying value is still nil, but the underlying type is not the nil type, so the comparison fails and we get false. So now we know what Go is doing. Interface nil comparisons include the underlying type. And there's a few reasons why we can't just ignore that underlying type when comparing interfaces. So first, we need the underlying types to be identical to ensure we're using the same rules for comparing two values. Remember, Go doesn't allow you to compare two different concrete types. If you could, you get the situation that we have in JavaScript, where whether or not two values are equal can depend on which side of the equal sign they happen to be on. Second, let's remember our example with the method on the nil variable. So let's define an interface for that method called number. And in main, we declare a variable t of type pointer to t, declare a variable n of type number. And running this code returns true for t, because for t equal to nil, and it prints out 2 for calling t.num, as we saw before. Didn't assign a value to n, so it's also nil. And we've commented out the n.num line because if we didn't, the code would panic because there's no underlying implementation to actually call. So let's see what happens when we assign t to n. When we check to see if it's nil, it's going to say false. But now we can call the num method on n and get 2 back, because the underlying t type has an implementation. If we didn't include the type as part of the nil comparison, we'd have an even bigger what, because sometimes nil interface would have an implementation, and sometimes it wouldn't. So I don't really much like the current interface nil behavior, to be honest. I can't quite come up with a better solution that fits in with other Go features. So all we can really do is just be aware of this and just be careful. So on to our last what. What does this code do? So yes, we are assigning true the value of false, and then we are printing it out. Does this A not compile? Oh, please, let this not compile. Does this B panic? Who thinks this code is going to panic? Yeah. C, who thinks it prints out true? You got to vote for true. All right, brave soul. All right, D, who thinks it prints out false? Oh yeah, D, this prints out false. What? You can redefine the meaning of true. And actually in Go, you can. Well, kind of, right? And actually, we've already talked about this what. So Go is a small language with a small set of keywords, only 25 of them. It's absolutely illegal to use any of those keywords as an identifier in your Go programs. But in addition to the keywords, Go also has a bunch of built-in identifiers. And they include types like int and string and bool. They include built-in constants like true and false and iota, built-in functions like new and close and make and delete, and a built-in zero value, our friend nil. So where are those names defined, and where do they get their values? Well, all the built-in identifiers are found in the universe block. And the universe block is the topmost block for all of your code. It's automatically part of your program. So remember our shadowing what? We had two different variables with the same name in a function, one directly inside the function and one in the for loop. Well, Go lets you shadow all the way up to the top. So you can shadow package block identifiers in your function block. You can declare variables in inner block that shadow functions block or package block. And yes, you can declare variables in the package or in a function or in a block inside of a function that shadows identifiers in the universe block. So shadowing universe block identifiers lets you do all sorts of interesting things. You can make int into a string. You can make a function called new that doesn't instantiate pointers. You can even redefine what nil and iota mean. And everything else in the same scope as your shadow declaration sees your declaration. If you add a package level variable or type declaration that shadows a universe block identifier, everything else in that package, even in other files, they're going to see your shadow declaration. So this is terrible, right? Anyone disagree? Go vet-shadow, go metalinter, none of them actually catch this. And if you think about it, shadowing really stands out as a what in Go. So in the name of understandability in Go, you can't define new operators or overload operators. You can't overload the meanings of functions or methods. But you can define new meanings for built-in types and constants and functions. And hey, that's all good, right? So every Go-to discussion starts with a list of new features to add. Personally, I want to start with something to remove. Get rid of shadowing, please. All right, we're almost out of time. Hope everyone got something out of this. What's are fun, but what makes them great is that what's teaches how Go does what it does. We look at how they behave and interact, and we understand the decisions and trade-offs that are made when you create a language. So the next time you run into something weird in one of your programs, write some tests, explore what's going on. You can turn that what into a how and a why, shrinking your weird problem down to size. Thanks for coming.